We are now looking at related rates and how to solve related rates. And so these are all going to be applications. I think all of the ones that we're dealing with are dealing with time. So let's think about, before I even go through these strategies, let's just think about an application. So let's say that there's some oil spill, maybe off the coast, southern coast, Long Beach area. And there was this oil spill. And when it started, right, it started maybe with just a dot. And as the oil poured out the pipes, it continued to grow, right? And so as it continues to grow, that has to do with time. And we could stop this, let's just stop it at a frame of time, and we can look at the area. And so we can also look at the radius. If we look at the radius, think of it that when we started that oil spill, that radius was, well, basically, I don't know, 0. And then it's going to continue to grow, right? And as that radius grows, so does the area. And so both of those are in terms of time. Our radius is growing within time, and the area, in this case of our oil spill, is growing in terms of time. So we are going to use, when we are doing these word problems, if we ever see the word, it grows at a rate of, rate deals with derivatives. So that should clue you in right there. That is talking about a derivative, a rate of change. The other thing that you want to think about when we're dealing with these, I'll give you the strategies in a second, but when we're taking derivatives, we want to, when we're taking the derivative, because our radius is in terms of time, we have to think about using implicit differentiation, or in this case, the area is expanding with time. We're going to have to think of this when we're taking the derivative that of the area piece that is in terms of time, and we're going to use implicit differentiation. Okay, so that being said, let's go through the strategies of solving these. And then we'll do lots and lots of examples, as many as I can within this class period. So related rates problem strategies, we're always going to first draw a picture and name the variables and the constants. So we're always going to have some sort of picture that we can draw, and we'll denote our variables and what we know. We're going to use T for time, and we're going to assume that all variables are differentiable functions of time. Okay, so then once we draw our picture and we determine what our variables are representing and put that in our picture, we're going to write down a numerical information in terms of the symbols of the chosen. So we're going to find some equation that represents the information that we're talking about and what we're trying to find. Write down what you're asked to find. Usually it's a rate expressed as a derivative, and usually a rate at a certain specific time. Write an equation that relates the variables. You may have to combine 2 or more equations to get a single equation that relates the variables whose rate you want, the variable whose rates you know. Okay. We might have to solve, we might have multiple equations. We might have to do the substitution method. We might have to solve for one variable and plug it back into the other equation. Once we've gotten this all set up, we're going to differentiate both sides of our equation with respect to time. And then we're going to express the rate you want in terms of the rates and variables whose values you know. So once we take in the derivative, we're going to look back and we're going to find out where does it say this is rate of change. That's the derivative. And then we're going to be able to plug that number in if it's given us a value into our equation that we just took the derivative of. And then we're going to evaluate, use known values to find the unknown rate. I guess I kind of stated that from number 5. Okay, so let's start out with a simpler example just to get the feel. And then we're gonna jump into some more difficult problems. So by request, or from the feeling I got from the other week, I'm gonna pull in some questions that are directly from my math lab that are similar to what you guys have. Okay, so the example in front of us, says, suppose that a dimension x and the area a equals 8x squared of a shape are differentiable functions of time. Write the equation that relates dAdt to dx dt. Okay, this one basically, we basically have some, this is dimension of area, and it tells us that the area is equal to 8x squared. I'm thinking to myself, these are a function of t. And so if this helps you, for right now, let's write this as a of t equals 8 all times x. X is a function of t, so x of t, quantity squared. And so when we come in here and we take the derivative of both sides, and so I'm just going to denote that I'm going to come in and take the derivative of both sides. So I have d dt of my area function a of t is equal to the derivative of 8 all times x, which is the function of t, x of t, quantity squared. And so when I take the derivative of a of t, I get back the derivative a prime t, or because of our notation in here and how it asked, I'm just going to say this is the derivative of a with respect to t, dA dt equals. So when I take the derivative of the right-hand side, I need to think of this as the chain rule. And the outer function in here, I can think as 8 of something squared. And so doing my general power rule, 2 my power times the 8 in front, that gives me 16 times, I have the inside, but this is raised, subtract 1 from my exponent. So it's going to stay the same. It's going to stay the same. 2 minus 1 is 1. And then take the derivative of the inside. So the derivative of x of t is x prime of t. And I'm going to write it dx dt, derivative of x with respect to t. Okay, so this function normally didn't have the x of t in here. The x, I put x of t just to reiterate that this is a function in terms of t. And so let's go back in here, and we know that then our derivative of our area with respect to time, the rate of change of our area with respect to time, is equal to 16 times x dx dt. The rate of x with respect to time.
I love the fancy lingo.
I'm trying to keep the math terminology in there so you guys get really familiar with it. Hopefully you start to get familiar with what I'm talking about. And you can use it too and impress some of your friends that haven't taken calculus before. So there was a question about me, why I wrote this as x of t. And it was to kind of hammer down the point that this x of t is a function in terms of t. Just like a lot of times y we write as f of x, and f of x is some function in terms of x, with just x on that side, an explicit form. And here, x is some function of t. And so Now, when we do these problems and we differentiate both sides, we're going to use implicit differentiation, but we have to worry about both variables that we're taking the derivative of. Those are both in terms of t, and we have to take the derivative of the inside. Before, when we were looking at implicit differentiation, we were only worried about when we saw the y in that term and we took the derivative with that y piece, we had to think of it that we were taking the derivative of the inside dy dt. But when we had the variable x, before we didn't have to write dx dt. Now in this section, we're going to be doing that. So all of our different functions are in terms of time. And so when we take the derivative of that variable, normally I won't have x sub t in there. You have to take the derivative of the inside. So the next example says, assume that all variables are implicit functions of time. Find the indicated rate. And we're given that our equation is x squared plus 5y squared plus 6y equals 17. We're given that dx dt is equal to 7 when x is equal to 3, y is equal to -2. And we want to find, which color we use? We want to find dy dt. Okay, so we want to start by taking the derivative of both sides of our equation. Again, x is in terms of time and y is in terms of time. If it helps you to think of that in terms of time, then write it as a function x sub t and y sub t. Okay, so we're going to take the derivative of both sides of the equation, and I could denote that I was doing that by d over dt of both sides of the equation. But now I'm just going to go and start taking the derivative. And so the derivative of x squared, that's 2x, but I took this derivative of x with respect to t, so I have to write dx dt. Plus, now let's take the derivative of 5y squared. So the derivative of 5y squared is 10y, but y is a function in t, so we're going to rewrite dy dt. Plus 6 times y, the derivative of that is just 6. But that was in terms, that derivative of y with respect to t. Equals derivative of a constant, 17 is 0. So we're trying to find dy dt. Now notice there's two terms that have dy dt. We want to isolate that on one side of the equation so that we can find that. If you want, you can. Right now, we also have what dx dt is, though. So we could plug in what that value is. That's 7. 2 times x, but x is given to us to be 3, right? That one's always. Plus 10 times y, but y was told to be -2, dy dt. Plus 6 dy dt is equal to 0. So I could have waited until the end and got that dy dt by itself, just like we had been doing before. Get everything else to the other side and just have dy dt equals, and then plug in those values for our variables and rates of change. Or I can plug it in now and just kind of simplify and solve for dy dt. Either way, you're going to get the same result. So I have 2 times 3, which is 6. And then that 6 times that 7, that's going to give me 42. 10 times -2, so this is -20 dy dt. Plus 6 dy dt. So think of those like or like variables, like terms, and this is equal to 0. So let's subtract 42 on both sides, and then we can combine negative 20 dy dt plus 6 dy dt. That gives us a negative 14 dy dt. Is equal to, so subtracting 42 on both sides, so minus 42. Let's divide both sides by negative 14. And those are both divisible by 7, and they're actually divisible by 2 also. So 14 goes into 42 evenly 3 times. And so we get dy dt is equal to, and 2 negatives make a positive, is equal to 3. Okay, so here are cases where we're given the equation, we're given what our values of our variable were, what our rate of change was, and then we just had to plug it in and find it. So now we're going to look at applications where we have to figure out what those equations are, what we know, which ones are rates of change, and which ones aren't. Next example says, when a circular plate of metal is heated in an oven, its radius increases at a rate of 0.01 centimeters per minute. Oops. At what rate is the plate's area increasing when the radius is 45 centimeters? Write the equation that relates the rate of change in area to the rate of change in radius. So dA dt equals what? dr dt. Okay, so first step, right, was to draw a picture. So we have some plate in the oven. And we know that that plate is getting hot and it's getting hotter. This radius is going to grow, right? As that grows, and we know it's growing at a certain rate. Okay. And this tells us that the radius increases. So if something is increasing, our derivative is going to be positive. Sometimes we're looking, maybe this was cooling down and maybe it was decreasing, then our derivative is going to be negative, just to be aware of that. So this is telling me the rate that this is, keyword rate, that this is changing. And so I know here that my derivative of my radius, dr, with respect to time, dt is equal to 0.01. When I put this in, I'm not going to put in centimeters per minute, but it's helpful to know that. And we want to know at what rate is the plate's area increasing. So we want to find the area, the rate of change of the area, so dA dt. And we want to evaluate this. It tells us when our radius is 45 centimeters. Okay, so we have our single picture and we know that that radius is continuing to grow as that plate heats up. And we're looking at when our radius is 45. And so you might have to go and look up, these deal with a lot of geometry, how to find the area of the circle, but that one's not too bad, right? That one is pi r squared. And so we have our area is equal to, first, before we put this in, we want to take the derivative of both sides. So let's take the derivative of both sides. If I take the derivative of a, that is 1 times dA dt. Is equal to, so if I take the derivative of pi r squared, r is in terms of t. So let's bring our 2 down front. So that would give us 2 pi r, subtract 1 from our exponent, so it's just 1, times the derivative of the inside. And our derivative of the inside is dr dt. And we want to find dA dt when r is 45. So we know r is equal to 45, but we also know what dr dt is. We know our rate of change is 0.01. So we're just going to go in here and plug that in. So this is equal to dA dt, the rate of change of our area with respect to time of the plate heating up, is equal to 2 pi times r. R in this case, we wanted this at when the radius was 45 centimeters. And the rate of change we know is 0.01. I'm going to leave pi in here just to make it exact. And then we also want to put in our units. Well, we know 2 times 45 is 90, right? And if we're going to multiply that 90 by 0.01, that just multiplies 90 by 1, but then moves my decimal over twice. And so my decimal is going to be 0.09. And so this was going to equal 0.09, right? 90 times, not 0.09, 0.9. I had to write it out. I might have said that. Times pi. And our area, it's growing, centimeters squared per minute. So our next example says the length L of a rectangle is decreasing at a rate of 6 centimeters per second, while the width is increasing at a rate of 6 centimeters per second. When L equals 6 centimeters and W equals 15 centimeters, find the rate of change of the area, the perimeter, and the length of the diagonal of the rectangle. Determine which of these quantities are increasing, decreasing, and constant. Okay. So let's write this. We have some rectangle. Oops. Like that piece. And we know that it tells us that the length of the rectangle is decreasing at 6 centimeters per second. Okay, so this is a rate of change. And so we know that the derivative of our length at time t, this is equal to negative because it's getting smaller. Centimeters per second. As that's shrinking though, and I kind of like, oh, well, it doesn't matter. And so as that's shrinking, our width is increasing. And our width is increasing at a rate of 6, it's increasing, so it's positive centimeters per second. Okay, so we are looking at the rate of change of our area, the perimeter, and the length of the diagonal of the rectangle. So there's a couple different things that are going in here. So let's look at first the perimeter. So we need to think about our perimeter of a rectangle, and we know that's twice the length plus twice the width. And we're actually looking at this at specific cases when our length, which I had this way, our length was equal to 8 centimeters and our width was 15 centimeters. Okay, so let's look at this and let's go through and take the derivative of both sides. So our perimeter's changing with respect to time, the length's changing with respect to time, and the width is changing with respect to time. And so when we take the derivative of that piece, we have to think of implicit differentiation. So the derivative of P is 1, and that's dP dt. This is equal to the derivative of 2L. Well, derivative of 2L is 2 times dL dt. Plus the derivative of 2W, which is 2, but that's with respect to time, dW dt. And we want to find the rate of change of our perimeter. Well, if one is, well, it makes sense. If one is increasing at a certain rate, but the other one is decreasing at the same rate, then the rate of change of our perimeter, it's not going to change. It's going to be 0 here. So we have dP dt is equal to 2 times the derivative, the rate of change of our length, which is 6 centimeters per second, plus 2 times dW dt, what that is shrinking, so negative 6 centimeters per second. And so simplifying, this is equal to 0. So the rate of change that our perimeter is changing is 0 centimeters per second. So it didn't even matter in this case where we were looking at. Anytime we looked at this, we didn't even have to plug this in this case. The rate of change of the perimeter is 0. So now if we want to look at the rate of change of the area, so our area of a rectangle we know is length times width. We have to be careful here when we're taking the derivative of both sides because we have a product. So we need to use our product rule. I'm going to move over just so we have a little more room. And so derivative of A is 1, but it was with respect to time. So dA dt equals, well, if I look at the derivative of my first, my length, that would just be 1 dL dt times my second function w plus my first function L times the derivative of w, but the derivative of w is 1. Derivative of the inside is dw dt. So the rate of change of the area at time t is 1 all times dl dt. Well, we were given the rate of change of our length was decreasing, so it's -6 times our width. Our width is 15 centimeters plus our length, but our length, what we're looking for is at 8 centimeters. Really don't need the one there. And dw dt, the width is growing at 6 centimeters per second. So we have enough information that we can find the rate of change of the area with respect to time when our length is 8 centimeters and our width is 15 centimeters. And so -6 times 15, that is going to believe is -90. Plus 8 times 6, which is 48. So this is going to be negative, which means that my area is decreasing here. And this is -42. And we're doing centimeters squared per second. And then let me just make sure there was nothing else. The last piece was the length of the diagonal. And so the length of diagonal we have here. Maybe call it D for diagonal. So that diagonal is going to be changing as that length decreases and the width increases. So what do we know about the diagonal? We can use our Pythagorean theorem. In these, you're going to see a lot the use of right triangles. And so we know that our diagonal, so we want to find actually that diagonal and derivative dd. Maybe let's call it C. Hypotenuse. Let's call it C. Okay. So we want a rate of change of our diagonal. So dc dt. That's what we're trying to find. Okay, but we know that our diagonal, c squared, this is equal to, right, one leg squared plus the other leg squared. Well, c is equal to really the square root, and I'm going to write it as a power because we're going to have to take the derivative. So we might as well write that square root of both sides as raised to the 1/2 power. Okay, so we found our equation that we need to use for the rate of change of the diagonal of that perimeter. And so now take the derivative of both sides. So derivative of c is 1. I'm just thinking to myself, did I really have to take the square root of both sides? And myself said, no, Erica, you didn't, because technically we could have just used implicit differentiation. And then we wouldn't even have to use a chain rule. So let's make our life easier. We have those tools now. Sometimes you just don't see them. Okay. Okay, so let's take the derivative of c squared, which we know is 2c. But our diagonals with respect to time, so it's dc dt, is equal to derivative of L squared is 2L, but the derivative with L with respect to time, so dL dt, plus the derivative of 2W I'm sorry, W squared, which is 2W with respect to time, so dW dt. The only difference here is, what is my only difference here? I have to divide both sides by 2c, and I actually have to do a little bit of work to find what c is, because we already know what we want our length and width to be, right? And so we had our length of 8 centimeters, and we had our width of 15 centimeters. And so we can use that Pythagorean theorem and figure out what C is for those lengths. And so C is going to equal the square root of 8 squared plus 15 squared. So that's the square root of 64 plus 15 squared, I believe, is 225, but let me just check. Yep. So C is equal to the square root of 289, which I don't think is a square root. Oh, it is 17. C is 17 centimeters. So we needed that piece right here because we have a C in here now. Okay, we got to just go back in, plug in what we know for the rates of change for L, W, C, and get dC over dt by itself. And then we're done. Notice if you divide everything through by 2, that will cancel out, right? Because every single term has a 2 in common. C, I'm just going to put it in, is 17. I'm trying to solve for dC dt is equal to my length. My length in this case was 8. Just want to make sure. Times dL dt, that rate of change of my length. That one was negative 6. Plus W in this case was 15, times the rate of change of my width, and the rate of change of my width, that was positive 6. So I have 17 times dC dt, or let's just divide by 17 right now. And then we'll simplify. So we get dC dt. The rate of change of our diagonal with respect to time is negative 48 plus 9d, because 8 times negative 6 is negative 48, plus 6 times 15, which is 90. So that's positive 42 divided by 17. Which doesn't go in evenly, so let's just leave it like this. Or it goes in 2 times, it might make more sense. So 2 times 17 is 34, that would be 8/17. And its rate of change, so the rate of change, and it looks like it's positive. So that diagonal is growing at a rate of change of 2 8/17 centimeters per second. Okay. So that was kind of a good problem in the fact that it took one thing we know about rectangles and it looked at multiple different things: perimeters, area, diagonal. Let me pause here.
Is it still centimeters?
Yeah, so it's still centimeters because both of our lengths and our widths are centimeters. And if we're talking about diagonal, that's not gonna, we don't have to worry like area centimeters squared. That length is
Okay.
centimeters. Yeah. But when we were looking at area, we have to be worried about our units. Or you got to worry about volume also. Something cubed.